In exercise 1.3, you calculated the field generated by an electron circulating in a 1 angstrom radius orbit at a distance of 3 angstroms from the center of the orbit. These values are typical for an atom in a transition metal crystal. Part A, to what Curie temperature would this field correspond? Part B, you also calculated the dipole moment of the electron. To what extent would your calculated magnetic moment be affected by an external field of, say, 50 oersteds? Use E is equal to minus m dot h and compare the result with thermal energy, kT, at room temperature. Okay, so first of all, let's go to this problem 1.3, where we have calculated the field of an electron that is orbiting with a radius 1 angstroms and at a distance of 3 angstroms from the center of the orbit. So this is what we had, and we have used the result for the circular currents to calculate the magnetic field at a distance a from the center, and when we did this calculation, the field that we have found was 47,434 ampere per meter. So we're going to use this field to calculate the Curie temperature of this solid. Okay. So now we're basically assuming that we have a PHYS molecular field, HW, of 47,434 ampere per meter. So this is the result from exercise 1.3a. Using this result, we will find the Curie temperature. From the previous problem, remember that the Curie temperature is, if we're using SI units, mu0 m PHYS molecular field divided by 3 times the Boltzmann constant. Here mu0 is 4 pi 10 to minus 7 Henry per meter, permeability of free space. And what is the magnetic moment of this electron? That we have also calculated in that problem. So if we look at the result of this problem, we have seen that the magnetic dipole moment of the electron was basically a Bohr magneton. So it's minus 9.4 10 to minus 24. That is roughly the Bohr magneton. So it's a Bohr magneton in z-hat direction. That's what we have found. Okay. So we're going to use this magnetic moment, a Bohr magneton. And the Boltzmann constant, we know, is 1.38 10 to minus 23 joules per Kelvin. So substituting these numbers here, 4 pi 10 to minus 7, Bohr magneton 9.274 10 to minus 24. The PHYS molecular field, we use 47,434 divided by 3 times 1.38 times 10 to minus 23, and this gives us a Curie temperature of 0.013 Kelvin. So you can see that this is not quite right. We obtain a very small Curie temperature. So the PHYS molecular field is not basically coming from this electron orbiting in a circle, because the field generated by such an electron is very small, and the corresponding Curie temperature would be very small. So basically that's what we learn from this exercise. Now we will compare the magnetic energy minus m dot h with thermal energy for this electron. The calculated dipole moment of the electron was a Bohr magneton. Well, roughly a Bohr magneton. So the Bohr magneton mu b is 9.274 10 to minus 24 joules per Tesla. Then we have a field, applied field of 50 Ersteds. 50 Ersteds corresponds to 50 times 1000 over 4 pi, or 79.6. We have 3979 ampere per meter. We have the energy, magnetic energy, minus mu 0 m dot h. I'm using SI units here. This gives me minus 4 pi 10 to minus 7 times 9.274 10 to minus 24 joules per Kelvin times 3979 ampere per meter. So the energy we find for this magnetic moment in this field is minus 4.637 10 to minus 26 joules. It's a very small energy. Now, how about the value of kT at room temperature? This is 1.38 times 10 to minus 23 joules per Kelvin times 300 Kelvin room temperature. Roughly, this is going to give me 4.14 10 to minus 21 joules. So this is the value of kT at room temperature. Now you should remember that the kT value at room temperature is basically 1 over 40 electron volts. So we could have used this instead of remembering the value of the Boltzmann constant. So this is the quick way to remember the kT value. Okay, so what is the conclusion? The room temperature thermal energy is 5 orders of magnitude larger than the dipole energy. So this 50 Ørsted is not sufficient for ferromagnetic alignment, because the moments that are interacting due to the fields created between them will be subject to this thermal energy, and therefore they will be randomized. All right. So the result is that the room temperature thermal energy is 5 orders of magnitude larger than the dipole energy, so a magnetic field of 50 Ørsted is not sufficient for ferromagnetic alignment. Well, this is basically the Zeeman energy of these moments that we calculate in this magnetic field, the magnetostatic energy. This energy is 5 orders of magnitude smaller than the thermal energy, and therefore, in order to minimize the energy, we cannot say that the system will have ferromagnetic alignment, because subject to thermal energy, they will be randomized. Okay. So we have used a previous result that we obtained in exercise 1.3. An electron that is orbiting in a circle with a radius 1 angstroms at a distance of 3 angstroms from the center of the orbit creates a magnetic field for 47,434 ampere per meter. So if we take this as the PHYS molecular field and we calculate the corresponding TC, it's very small. So this clearly is not the correct way to do it. And when we calculate the magnetostatic energy of this electron in a field of 50 oersats, we see that the Zeeman energy is very, very small and compared to the thermal energy. Therefore, we cannot expect ferromagnetic alignment of these moments, and they will be randomized due to thermal energy. Well, at least for the case of room temperature.